Welcome everyone to our next episode of the Coffee Breakdown podcast. Today, our special guest is Lorenzo Zanisi, who is a data scientist working for the UK Atomic Energy Agency. He's done previously a PhD in astrophysics, where he combined astrophysics with ML models and statistical modeling. And so today, we're here to bring him on to talk about both that work and how machine learning is going to, or should be applied to science moving forward. So welcome, Lorenzo.
Thank you. Thank you very much for having me today.
Yes. So, I did forget to mention that of course, you did your PhD in astrophysics, but now you've moved forward to work on fusion. So it's a very interesting mix of just different fields and different concepts. So I guess the first question I have to you is, well, what do we mean with machine learning? Like, what is that, and how do we apply it?
So machine learning is a tool, basically a computer program that learns with data, and more specifically, given some data, the computer program learns automatically without actually being told it's told what the learning task is, but it's not told what it actually has to do to perform the learning task, to perform the final task, which is, for example, a classification or a regression. And this performance and the performance of the algorithm at doing this task improves with time and with the more the data the algorithm is fed. So this is particularly relevant in the age where we live today, which is the age of big data, where every kind of data is collected. Want it or not, Google collects our data, Amazon, Facebook, they all make their nice machine learning models, predictive models of how we behave, what we like, and so on and so forth. And but the thing is that for science, this is also true. So we have big experiments in a lot of the scientific domains. So, for example, if I think about my background in astrophysics, there are new facilities like the LSST, which is a telescope optimized for transients. There is Euclid, a space mission that will study galaxies, and many others that will collect a tremendous amount of data. And this data cannot be looked at by humans. you need a computer to process them. So this is the other advantage of machine learning, that it can sift through data much quicker than us, simply because, well, it is backed by computing power. We could do all the calculations that neural networks or other machine learning algorithms do by hand or with a calculator. But it would be much slower. We would achieve the same identical results in the end, but it would take millennia for us to do that. Instead, powered with a computer, we can do all those calculations much faster and sift through data much more efficiently.
Okay, so I mean, this is interesting. Well, of course, machine learning holds a dear place in my heart as well, being part of my PhD project. So when we talk about machine learning, it's really how we process data, right? So it's not necessarily that, as you mentioned, that there are two, let's say, use cases. One is just processing large amounts of data, right? So if you have a machine learning model and you just want to sift through a large amount of data to get at the trends behind it. But the second thing is then the pattern recognition itself, right? To then identify that there are trends in this data and to kind of give you a more condensed version of the large data to say, like, okay, there's something here that you may be interested. But one of the confusing things that's always, of course, I would say something that I've had to, or people have asked me and I don't really have an answer for, is like, well, how does the machine learn, right? Because of course we give it all this data and it's supposed to somehow figure out combinations of these numerical these numbers effectively. How does it do that, right? Like what in the end, it's still trained for a goal, and we still have to specify the goal, right?
Yeah.
So I guess is this and a lot of people are confused on that. Like, how do we choose a goal? Do we have to choose a goal? Is this something that is machine learning equal artificial intelligence, equal, something that can be self-directed in terms of figuring out its goals as well? Is that what we mean when we say machine learning, or is it something a bit more defined?
Yeah. So machine learning is more of the tool with which you would achieve artificial intelligence in a
Mm,
way. So artificial intelligence somehow encompasses a broader scope than machine learning. So imagine, for example, we have a machine learning algorithm that classifies I don't know cancers versus non-cancerous cells or something like that. Okay, well, a particular kind of cancer that is something that is very good, but we would never dream of calling that intelligence, right?
yeah.
This is just one little part. Humans maybe could do that task, but actually, in a lot of tasks, machine learning is a lot more specified that human intelligence. And so it can achieve even performance that is superior to human intelligence. Now there's the question of whether these of whether actually achieving human intelligence requires a human brain, or whether the machine learning algorithms that we have, including neural networks, uh, are already enough if pushed enough to achieve general artificial intelligence. But I'm not going to go in that direction because
Hmm.
I because I realize it's a very very far away from your question. Um,
Well, it
so
might be a question we approach later,
oh,
but I
yeah.
agree. Yeah.
So there's a yeah, in terms of the actual learning, the learning is done given an objective. So you have, for example, what is called a loss function. For example, I'm thinking of neural networks. You give a neural network a given objective. For example, minimize this or maximize that. Well, typically it's always minimize something, and the neural network basically will propagate the information from the from the output. So given some examples, some training examples, the neural network will make some predictions. This prediction will feed into your loss function, which is essentially what you are hoping to achieve, the objective that you're hoping to achieve with your learning, with your algorithm. And then basically the information of the discrepancy in a sense between your prediction and your target, the something that some data for which you already know the answer for, that information is propagated back into the neural network, and the parameters of the neural network will be adjusted according to that specified objective. um, and yeah, this is mostly how neural networks work, for example.
Right. So, like, just from my mind, and I mean, the parallels are, of course, there, is that we can see this machine learning model as you know, a very high dimensionality fit, right? It's just like least squares fitting, but of course, a bit more in depth and a bit more, let's say, robust than that. But it is effectively the same thing. It's just a regression fit. But then this brings up a different question, is that, well, how is machine learning and all of the tools around machine learning different or maybe the same as traditional statistical modeling, right?
Yeah, so this is an interesting one. I think that the particular example that you make about regression is particularly suitable um, to this conundrum, let's say. But when we and I'm gonna deal with this in a second, but I just wanted to say also that for example, statistical models wouldn't be able to do things like natural language processing to the level that deep learning models have achieved, and even my grandma knows what ChatGPT is, right?
Yeah.
So um, so yeah, there's definitely some parts of machine learning that statistical models just are not suitable for, and in general, this is due to the fact that statistical models um, kind of try to answer a different question, I feel, compared to machine learning. So statistical models are concerned more with inference, and machine learning is concerned more with predictions.
Hmm.
So
So
statistical
maybe,
models, you wanna test an hypothesis. You wanna say something like, is this data linear? Does
mhm.
it follow a linear relationship, or is the true data generating distribution a Gaussian mixture with these parameters for the mean and variance of each Gaussian? Instead, machine learning is more concerned with what can I say about the properties of this particular data point that I have not seen before. Okay, so for example, if I think about a concrete example of, let's say, classification. Okay, you have some uh, you have some um, you have some coins that some of them are blue, some of them are red.
Mhm.
You scatter them on a plane, okay, and then you can build, for example, a logistic regression model, multivariate logistic regression model, to just like find the separation between these two data sets, okay.
Okay. Mhm.
um, and that is just going to tell you something about the separation between these data sets. But now imagine doing that with imagine doing that. So a neural network can do exactly the same thing. Okay,
Right.
it can do it in the same way. But now imagine doing that with images. Okay, you have images of cats and dogs.
Mhm.
Okay, typical thing that people used to do 10-15 years ago. You images of cats and dogs, and you have to build a logistic regression to find the optimal, separating boundaries between these two classes. This is insane.
Mhm.
Because there's just so much structure in the data, in the image. There's so much highly nonlinear correlations between various parts of the images, that is something that is very, very hard to see for a traditional statistical model, like logistic regression.
Hmm.
Okay. um, yeah, and also, yeah, you're not necessarily concerned with when you have image data, for example. You're not necessarily concerned with testing whether what does it even mean to test whether an image, when you do regression on image data, for example, and you can do that, but what does it even mean to the relationship is linear between your image and the particular label. That's not something that is really even an interesting question from the statistical point of view, right? So I'm thinking, for example, of this work that I used a lot in my PhD, where you have galaxies, and the kind of class of galaxies is treated as a regression problem. So each galaxy is assigned a number from
Mhm.
-5 to 10, where -5 is an elliptical galaxy and 10 is a very is a very regular galaxy. There are disks in between of various irregularities. Now, what does it mean to want to test that the relationship within this image and number is linear?
Hmm.
Is that an interesting question? Not particularly. We just want to have a predictive model of whether this is a -5 or a 2 or a 3.5 or something like that, because we want to use that information for downstream tasks. So
Right.
it's a very different idea, I think.
Okay, like, so maybe just so to see if I got the idea, is more that machine learning cares more about the outcome
Yeah,
of the
that's
learned
right.
model, whereas traditional statistical models care more about the relation defined by the model, right? So
Well,
not
yeah,
necessarily the outcome, whether it's correct or not, but like the actual relation between the input data and the output data.
for example, yeah,
Yeah.
but not necessarily just limited
Okay.
to that.
Hmm.
But for example, you're interested in saying something about statistical significance, for example,
Hmm.
of something, which in machine learning, it's not necessarily what you want to see. In machine learning, you have, for example, positively or negatively labeled samples, or you want to try to do some anomaly detection, and you're not going to get a p-value from that,
Uh-huh.
right? Which is instead what you would get for example, at LHC when you see a strange event, how many sigma away is that
Hmm.
from, what is the significance of that? So in machine learning, you would just classify that as an outlier event to be flagged for follow-up, but you wouldn't have a statistical measure of a p-value compared to some model.
Ah,
It's a different idea.
Interesting, because I always thought that machine learning, of course, has its roots in statistical modeling, or at
Yeah.
least the has shares some of the same mathematics. But then I thought there was work trying to build machine learning models that have that kind of like confidence interval type of information built into it, or is that just not possible?
Well, I, I think I think yes, but it's in a different way, in the sense that,
Hmm.
if I understand your question correctly, so there you can embed machine learning models with uncertainty. Is that what where you were going to go? Or no?
Yes, well, like I mean, you can build machine learning models with some measure of uncertainty, but I guess I'm uncertain whether or not that's the same type of uncertainty that is being tested for inside statistical, like inference, right? Or do they represent different things despite using the same terminology? Is more the question.
Well, so there are some so the things are a bit blurred in some cases. So, for
Mm,
example, if I think about some models like density estimation models, like normalizing flows, and these are basically models that tell you, what is the uh, data generating distribution of your data set. So imagine this as a big histogram.
mhm,
Okay, so imagine you have a 2D data set. You can make a 2D distribution over that. You make an histogram. Imagine you have images. Well, you make an histogram of images, and then you kind of do your normalizing flow to learn that big histogram in an interesting way. And that is going to give you, for example, if you want to do if you're concerned in inverse problems, for example. So you have a model, and you want to test that model on your data,
mhm,
then you can essentially learn the likelihood of your model, which is this big histogram, which is just like the sampling from many realizations of your model with different parameters and various correlations within the parameters that you put in your prior. And
mhm.
then, given some data, you can Bayesianally, but in a Bayesian way, you can
Yeah,
invert this model and find the parameter that you're interested in with some uncertainty. So, in a
right.
sense, um, in this sense, I guess this goes in the direction that you were suggesting. That is, some machine learning models can also give you inference of in a statistical sense, given a certain model of your world, which, for example, could be plasma states, or could be the universe, or could be I don't know what else.
Hmm. So I mean the inverse problem, of course, is interesting, is sort of saying that okay, if this is the outcome and this is my model, then what is the set of inputs or the distribution on the inputs that could have generated this output using
That's
this
right.
model,
Yeah.
right? But I guess that's a different question than what statistical modeling tries to answer, which is more like what is the statistical significance of this output? Like,
Right.
what is the chance that this output comes from the hypothesis you are putting forward versus something else, right?
Yeah.
So
So
these are different questions.
yeah. In that sense, then I don't think that, at least to my knowledge,
Mhm.
I don't know of any machine learning model that does that
Hmm.
really in that same sense.
Okay.
Do you? Maybe I'm missing something here that
No,
is fundamental.
I'm just curious because it seems from my side that there are people asking whether machine learning models can provide that type of, you know, p-value type significance. So if I run this type of data or this set of inputs through a machine learning model and it spits out an output, it's not just okay whether this output is meaningful, or sorry, whether this output is correct, but also whether that output is meaningful. And I think that that's what the questions people are asking me, but it may just be that they're confusing what machine learning is versus what statistical modeling is,
Yeah,
right?
I mean, I'm not sure. Like, if I think of a neural network, okay, a neural
Mm-hmm.
network has hundreds of thousands, millions, billions, even of parameters, right?
Mm-hmm.
Now, if I want to fit a linear relationship, okay, with a neural network with 100 billion parameters, I can do that.
Right. Right.
Every
It would take a
parameter
long
will be,
time, but yeah.
all the parameters will be
Yeah.
very, very, very small, apart from one
Yeah.
or two,
Yeah.
depending whether there's an intercept or not.
Right.
Okay.
Yeah.
Um, so now, what what are we trying to do there, right? So with a statistical model, we're trying to say, okay, this relationship is linear with a p-value of x, okay, and you impose your statistical model. With a neural network, I'm not quite sure whether the same kind of question makes sense to even be asked,
Hmm.
because the parameters of a neural network, can really be anything.
Right.
Right. So in this particular case, it will fit a relationship with, maybe what one thing that you can say is, well, in a Bayesian sense, you can maybe put some priors on your weights of the neural network, and then kind of derive what is the posterior of your output based on these particular weights. But I'm not really sure. Um, I'm not really sure that's going to answer the same identical question.
Hmm. Yeah, and I think what makes it hard to interpret a machine learning model that way is also the sheer number of free parameters it has,
That's right.
right? I mean, if you just try to apply a linear model to your data, then you have one or two free parameters. But then if you take a system which has like, 100,000 free parameters and try to model the same thing, it would like the answer could come out the same in terms of like the actual, if you were to take your model and then plot the output versus the input,
Mhm.
but the actual weights or the actual, the values of the free parameters in the model would be harder to interpret, if not meaningless, right?
Exactly.
Yeah,
That's precisely it.
I
Now,
see.
yeah. So that's yeah. That's just like noise at that point.
Right. And I think that one of the things that you mentioned earlier, which is what I wanted to ask you, is that really it seems to me that machine learning models excel when the input dimensionality is large. So
Mhm.
large that traditional statistical modeling it would take either forever, or because you have to examine every cross correlation between inputs as well, right? So is that a place where machine learning is, let's say, better or more applicable, or is that just a limitation of statistical modeling? And if it were possible to do statistical modeling with that high dimensionality in the input space, that it would be worth it to do both.
Um, that's an interesting question. So I think that definitely machine learning does better when the data dimensionality is higher.
Mm.
And that's because if you think, for example, of neural networks again, neural networks build a representation of the data. So they project with the various layers the data to different spaces, and so find somewhat, a more suitable space where things where the data looks nice, essentially, and
Right.
for example, looks more separable, or data regression can be performed more easily, and so on. So what happens in high dimensions is that the volumes become very big.
Mm.
So the volumes increase exponentially. If you think about volume of a circle, right, is r squared. The volume of a sphere is r cubed, and then in higher dimensions it goes exponentially with dimension. So essentially, what happens there is that for a fixed number of data points, it becomes harder and harder and harder to do any sort of inference. Imagine you have a coin and you have one line. You put a coin on one point of the line. This line is at a fixed length. You go up and down the line. Sooner or later, you'll find the coin. Okay.
Right. Yeah.
Now you have a football pitch and you have one coin. It's gonna be hard, but if you try hard enough, you're gonna find this coin. Now you have the International Space Station, okay, which is one football pitch long and half a football pitch like across, or something like that. And drop a coin there. No, go find it. And now imagine this, when you go to 4-dimension or 100,000 dimensions, that no real. Well, 100,000 is a bit too much. I don't think there's anything that goes to that dimensions, and any sort of interesting problem. But if you go to hundreds of thousands of dimensions, which so hundreds or thousands of dimensions, which is definitely the case for image data, for example, statistical models will really struggle to kind of capture all those. You basically have to give insane an insane level of you have to have a lot of knowledge of what your data looks like, essentially, to make a statistical model that makes sense in high dimensions. The problem is that in high dimensions it's really hard to visualize these things. So gaining a lot of data gaining a lot of knowledge about your data in high dimensions is really hard. And so basically there is also like a fundamental, like, human problem in trying to scale statistical models to high dimensions, because it's fundamentally hard to make hypotheses on what your data looks like in
I
high
see.
dimensions. While a neural
Yeah.
network or a support vector machine or a random forest, they just do their own thing and they find a way to optimize whatever objective you give them.
Okay, so it means, I mean, just from this conversation, I'm kind of getting the conclusion that machine learning models and the traditional statistical models answer different questions, or at least they're used to answer different questions. Their strengths are applied to different domains of questions. And I guess that is the next question, is more so like, what types of questions do each of them, well, I guess we already covered that. What types of questions are they better at addressing? But I mean, in terms of, now we get to the scientific part. So how can we use these models to improve how we do science, or even how we approach science?
Yeah. So for example, in my PhD, I did part of my PhD work was a statistical modeling of galaxy populations. And part of my PhD, and another part was machine learning models of galaxy populations. So when I dealt with the statistical models, it was mostly about finding what is the distribution of galaxies with a certain size and a certain mass and a certain rate of star formation. What does it look like? And then find basically the parameters of typically these things are Gaussian. Find the parameter of this distribution. Maybe it's a Gaussian mixture, and then try to then cross match that with models that we have and see whether they match his distribution. Spoiler, they don't.
Okay.
Yeah.
I don't know. I don't know if that's a good thing or a bad thing.
And so this is kind of what statistical models are. I mean, this is my experience with statistical models. And instead for machine learning models, in my PhD, I was learning the data. I was learning the data generating distribution of galaxy images with a neural network. So instead of saying, okay, this is the distribution of galaxies of a given size and a given stellar mass. Distribution in size of galaxies with a given stellar mass. This is a Gaussian. This is the mean. This is the variance. Perhaps there's another component here. This is it. Here I'm saying that this is a double Gaussian, okay, because the distribution is simple enough, is just one parameter, just the size, and then the number count. That's it. But instead, when you have things like image data, this is a completely different thing to do. It's very hard to try to do the same. But how do you do it? Like, do you do it pixel wise? You have 1,000 histograms, and how do you decide how these are related to each other? Like, it's a very, very difficult problem to try to visualize even. So instead, what I did was to build a generative neural network that basically learns the probability distribution of a particular of your population, and then you can say, okay, this image has a probability of this or that. Okay, so yeah, this is to say, for example, this is a clear example of where statistical models versus neural networks, with deep neural networks, can achieve results that are kind of similar in a similar idea, but then they have to be different tools. Okay, so this is different in that sense. And if I think about other applications of machine learning in science, there's there's been a boom, right, in the past 7 to 10 years.
Yes, absolutely.
Really.
Yeah.
So if you think that I was reading earlier while preparing for this the paper, the ImageNet paper from 2012, which has something like 50,000 citations. It's a bit ridiculous.
Yeah.
Or maybe even 10 more than that. I don't know.
Yeah. But it's really blown up since then.
Yeah.
Yeah.
And they were training, a 5-layer convolutional neural network on 2 GPUs. The RAM of each GPU was 3 gigabytes, and it took 5 days to train.
Wow.
Right.
Wow. Yeah.
And for us now, you do that, in maybe 20 minutes on an A100 GPU. So it's quite crazy, like how that paper or whatever was happening in those years, right? Completely revolutionized the field. And if you look, it was 10 years ago. Science doesn't progress that fast.
Right.
Usually.
Yeah, usually anyway. Yeah, no, this was like a real revolution. But I think it's also because the technology that came with it is useful as well, right? So like even outside science, because as you said, I think the for machine learning, the focus is more on the outcome rather than the trends. People and in terms of, let's say, actionable decisions, knowing the outcome is better than knowing the trends, because like I have this new machine learning model that captures within it all the trends. All I need to do is just query it for what's the next outcome. Like if this changes, what's the next outcome? And then I can make decisions based off of that.
So this is exactly. So whenever machine learning this kind of ties back into your question of like, when is machine learning better than statistical models? It's it also says that when data is really complex, when you don't really have a model for the data, right? You have to a model that explains the data in some way. You have to resort you have to be in a way happy with whatever you can do, which is just
Right.
predict. It would be
Hmm.
amazing if you could also do statistical, p-values and so on. And I'm sure that someone is doing that, but I just don't know about it.
Right.
Um, but when you look at, for example, the chaotic behavior of plasmas in a tokamak, and I mean, I'm sure that all the physicists, the other physicists listening to this would disagree, but do we really care whether we actually understand the physics of disruptions, or do we actually just want something that makes the plasma not disrupt? So a
Right.
reinforcement learning based model, for example, that learns what a disruption is, it doesn't really exactly know why that happens, but it's got data from previous experiments, knows what a disruption is, and learns how to mitigate that, or what kind of action to take when there is a precursor signals of a disruption that what the algorithm somehow captures and we can't. And I think that while it would be very nice to have also the physical understanding of what's happening, it also is important to be pragmatic. And I think that this is also the approach that was taken in other communities. For example, if you look at the drug discovery community,
Hmm.
right? Drug discovery is a very, very, very complicated task.
Hmm.
Okay, yet there are startups that do drug discovery with AI, and there are human trials with drug discovery with AI. We're very close to putting the first AI generated drug on the market for human consumption.
Wow. Okay.
So
Yeah.
this, I think that this is kind of what we should be aiming at for fusion. If people trust AI, and of course, these are all private startups that will never tell you how they did this.
Right. Yeah.
But we have to reason in the way that if people trust putting an AI generated drug into a human, uh, and this can be done safely, so safely that it can be commercial. Why
Mm.
can't AI be deployed, in a control system of a tokamak?
Hmm.
Right? Do we, obviously the challenges are different, and we're talking about two completely orthogonal fields, and so on. So the reason why we are not there yet is because all these challenges that are specific to fusion haven't been addressed yet. But I think that when they will be addressed, I think that we should not be shy.
Hmm.
And
Yeah.
let's
No.
go let's go
Absolutely.
forward with it. And
Yeah. Well.
then and then we can muse about the various instabilities and perturbations, and all sorts of things. But having a predictive model that can tell you how the plasma behaves, I think would be a no-brainer.
Right. And I think I would argue that most of science goes in that order anyway, right? You discover a new phenomenon, usually experimentally, and then you develop like a really phenomenological model. Like you start with an empirical one, and then you try to add some physics to that empirical model to see if you can explain the trend that is there in the empirical model. And then later there's some more fundamental theory that is either developed or adjusted to incorporate the new data, right?
For
But
sure.
it happens generally, at least I've seen, it happens along that timeline. Of course, there are circumstances where you have theory predicted discoveries first. So the theory says this should occur, and then later they develop the experiment to actually find it. But in most cases, it does work the other way, right? You can even think of this like high confinement mode inside tokamak plasmas, right? It's like somebody just found it inside Aztecs, um, and then from there, people develop this scaling law, which is the transition from the low confinement mode to the high confinement mode, and then all the tokamaks just started using that and found out that okay, it needs to be tweaked for these plasma parameters, or adjusted here and there for machine size. But that's what they used for the longest time, and we're still trying to figure out the exact fundamental physics of how this transition occurs. Of course, we have better ideas now, but people have been using H mode for decades already, right? So I can see that happening. And if machine learning can accelerate that, then I agree with you. That's extremely useful, right? Even
Yeah.
just building that empirical model that can predict better
But this,
is
but
useful.
this is super true, and but it's also true in the reverse. Like for
Mm,
example, imagine you have a complicated model, okay, and you don't really know whether it works. You have some, of course, they will be informed by previous models and previous experiments. You make a new model, and then you have to test it, right?
mm,
Imagine you can accelerate this model by making a surrogate of it in some way,
mhm,
and uh, and then you can deploy it at scale, over uh, all the kinds of data that are there from the various tokamaks and so on and so forth. And you have like this very general surrogate that you can just deploy on Jet, ASDEX, you name it. Okay,
mhm, mhm.
and at this point, you know exactly where the model is going to where the model fails because you have an accurate surrogate. It's fast to run. You can run it everywhere. You don't have to wait 3 weeks
Mm.
for for the model to run because you've done that previously. You've just like run whatever however many weeks of simulations to generate your training set
Yeah.
and build your surrogate, and then you can just deploy it, just amortized. Okay, and so once you do that, at this point, you know exactly the pitfalls of your model, and you can go back to it and refine it and
Right.
start from scratch instead of just like painfully, try to to find the shot or and try to learn. And of course, I know that there are very that it's very hard to actually do this and have set up a simulation campaign with simulations not breaking. So PS people, I'm talking to you here.
Yeah, yeah, yeah. No, but I mean, it's funny that you mentioned this because actually, this is what I'm currently working on, right?
I see. Okay,
Yeah, yeah.
cool.
This is my stuff where it's sort of we want to streamline the process of modeling for different plasmas so that we can just try it on everything. Of
Yeah.
course, accelerating the model is part of that component, the surrogate modeling and all this stuff. But then even building the pipelines to run the model on all the experimental data that we have to verify where it works and where it doesn't work. That's part of my work now is building that. So I totally agree with you because I'm trying to do it. Right? So I agree with that absolutely. But I think that yeah, it's like a different approach. It is
So
there's
what is really exciting, and here we're gonna go a bit on a tangent compared with
no
respect
worries. Yeah, yeah, no worries.
to the machine learning
Yeah.
specific part, but it's actually still machine learning because 80% of the machine learning is the data, right?
Hmm.
Everybody says that. Maybe 80% is a bit harsh, but certainly a large fraction of machine learning, the machine learning pipeline is dealing with the data. But for simulations, the data comes from computers, so we need the HPC resources. We
Hmm.
need to make our models. We need to make them faster. We need to make them able to run at the exascale, and in that way we can generate faster training sets and iterate even faster through the model data validation uh, side of things, and then improve on our models as fast as we can. And uh, and on the other hand, also from the data side, we need high throughput
Hmm.
if we really want to to process data in real time. We need high throughput infrastructure that allows us to do that. So there's again this is again HPC and clever databases and all things that I don't understand, but I know that are very important for these kinds of things. So it's really more of a uh, you know um, it's a very HPC generic, HPC specific task that encompasses many things from
Hmm.
from the simulations to the data to the storage to the streaming to the machine learning. Machine learning is a part of that,
Right.
but to concert everything, and this is an enormous task.
Yes, absolutely. And I mean, there are many people within Europe who are kind of working on it. And I think now that machine learning is becoming a bit more prevalent, not just in community or in society as a whole, but also from a scientific point of view, they're seeing the advantages of applying machine learning or using machine learning as a tool to accelerate science, then it gives a lot more emphasis to these tasks and projects to sort of like coordinate everything, build standard data structures that so that you can just plug and play different models, try to collect the data all in one place or at least on a set of servers, with high performance computing access to those servers, right? So all this sort of stuff and data permissions and all this sort of stuff, this more infrastructure slash bureaucratic level, it is occurring, but it is slower because it is not how we used to work,
That's right.
right, in the fusion field. So, but you're right, those are essential, and machine learning is just one component in this whole ecosystem, but it does require these other pieces to be put into place, or
I
else.
mean, I
Yeah.
don't think it's only a problem of the fusion field. Like some fields have done better than that. So, for
Hmm.
example, astrophysics, most data is open. You can just do an SQL query on whatever database that's online, and you get the data. And typically, there's embargo periods of 2 to 3 years, but then it's all available, and you can just do your own thing. Um, but for example, if you think about medical records of patient records, all of these things are in horrible formats that are
Right.
not usable at all.
Yeah.
And there's a really, like, the people that want to do machine learning on that kind of data really have a hard time trying to process that. And
Hmm.
but even if you think about other scientific or engineering really endeavors, like I don't know. I'm thinking about aerospace, for example. All the data collected there is still not really machine learning ready,
Hmm.
right?
Okay.
The data from a lot of devices, power plants, and so on. It can be really messy and not really ready to use.
Hmm.
And all of this technological revolution is happening, um, sorry, all the data revolution that drives then the machine learning revolution is only been happening recently, where people
Hmm.
have started to think about how to actually handle, and that's why you have all these new databases around that allow you to store and deal with data in a much nicer way.
So if I were to ask, just for people who are, let's say, not familiar with machine learning at all, like no hands-on experience at least, just like what they hear in the news, what do you mean by a machine learning ready data? Like, what do you mean by machine learning ready data?
Well, I mean that you need to have it needs to be fair, so it needs to be findable.
Hmm.
It needs to be, oh my god, now I forgot. I forgot what it stands for.
Yeah, it's
but
an
you
acronym,
work
right?
with
Yeah,
fair data too, so you can help
yeah.
me.
Oh no, I also do not remember all four of them. Yeah.
but
Yeah,
so it has to be findable and accessible.
yeah.
Okay, so you need to know where the data is, and you need to know how to access it.
Hmm.
You need to know, it has to be, what is the I again? And the R. Um, uh, God, this is putting me in a hard spot here. Can you Google that quickly?
I will to Google it quickly, but like maybe you just can maybe what is the purpose of fair? Like, why do we want it? Yeah.
Well, we want it because we want data to be easily usable, and we want everyone to be able to use the data to build their own models, and to challenge and keep going, essentially in a direction where the same data, which is reached from whenever when reached, with new data that is always coming in, that data is a common pool over which people can build their models, and basically open access data in a way.
Mm.
Well, not quite open access really, because you can still have um, some licenses on that, I believe, even
Hmm.
in a fair framework. Here I'm really out of my depth, so I apologize if I say something that is not that is not correct. But basically, my understanding is that you really want to use to have a common framework for everyone to work on, and
Mm.
let the best algorithm win.
Right. And I think so. I looked it up. FAIR is findable, accessible, interoperable,
Interoperable
and reusable.
and reusable. That's right.
Yeah.
Yeah.
So those principles, I agree. So like having fair data means that also that anybody who's interested in trying to develop a model has access to it so that they can make an attempt. And if it turns out to be better than everything else, then of course we should, try to use that model because it's just better. We all benefit from having people try these sorts of things. But I think even beyond that, or maybe it's included in the definition of fair, and I'm just unaware of it, is is there particular components of the data that need to be in place, or can you just like hand people a table of numbers, right? Because I have found that that's not really how it works. You can't just give people a table of numbers and suddenly they can magically machine learning model
Well, this is
magic it out of it, right? So
well, this is kind of the problem of interfacing science, any kind of science with computer science.
mhm.
That you always need to give metadata,
Mm.
and you always need to have some kind of you know some kind of domain knowledge of about what exactly that data means. So that means that you need to have some readme files, for example, or at least another human in the loop that helps you there, right?
Right. to
So yeah,
sort
there's
of
a
to sort of just make sense of the data and like get a feel for what is the question that is interesting to ask of
that's
this
right.
data, right? Yeah.
Yeah, yeah,
Hmm.
exactly. So I think, that's probably the main the main part. And most of the times, however, all of this comes in a really inconvenient format, where you have nested dictionaries, for example, where it's not really easily queryable, because all these nested dictionaries, you have to always go and find where the data actually is, and then export that to a table, for example, if you have a tabular data set. And
Hmm.
sometimes you might have corrupted data. Sometimes you might have and so all these data all these flags are really important. You want to really make sure to not throw away data, because all data is good data. But
Hmm.
also you want to make sure that for particular tasks, you do not use some data. So, for example, say you want to do anomaly detection, okay, in a particular data set. Okay,
Hmm.
you can throw everything in, do your anomaly detection, and then a posteriori say, okay, well, this is just the diagnostic here wasn't working. Clearly, it's only zeros. It doesn't make any sense. Okay,
Right. Okay.
and this is clearly anomalous compared to the rest. But
Right.
you don't want to use that when you do a regression task of sorts, because clearly that is broken data.
Hmm.
So this is an instance where it's useful to have the broken data for one task, but not for the other one. Well,
Right.
useful to have it for the broken one. Say like that would be like the first sift through the data to find things that are odd, I guess. Um,
Hmm. Yeah, that's interesting. So like, because I definitely agree with you on the point that it would be nice if the data is sort of like condensed into a ready to ingest format, like sort of like tables rather than a bunch of nested structures where you have to like loop through a bunch of lists in order to find your data. um, but the problem is often that then you need to construct that table specifically for a task almost, right? So you can't have a generalized structure that represents all data from a plasma device, let's say, that also suits the need of machine learning. And so you run into this problem between the two camps. The ones who own the data, produce the data, let's say, want to have a generalized format so that they don't have to play around with, how the data is sorted every time that they want to insert new data. But then on the other hand, such a generalized structure is not that useful, or it's at least very cumbersome for someone who just wants to answer a particular question, right? Because they have all this extra data that they don't know what to do with. The format is not very conducive to their algorithms, blah, 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 right? So there has to be a person kind of in the center whose job is to make the transformation, right? And having that person is just, there's no culture of having that person around.
That's correct. That's
Right?
correct. Yeah, the data. So we've got someone working on this, and
Right.
and is very good, but is a very hard is finding it very hard to deal with the way the data is currently formatted.
Right. And so I guess this brings up the question. I think we've already talked about it like here or there within the previous bit, is like, what sort of issues have you encountered in, bridging that gap between machine learning, like the data scientists and the computer scientists, and then the scientists who produce the data that you're going to work with?
Well, yeah, the first one is that a lot of the times there is no um, it seems like we're speaking different languages.
Right.
Because fundamentally, when I talk to people in the material science department, I'm not a material scientist.
Right.
So it's really the case, and when I talk to them, they're not computer scientists. So it's really the case of trying to really I'm gonna use a term that I don't like very much, but I can't find another one.
Right.
Dumb down,
Okay.
things.
Translate.
Translate, let's say. Yeah. So you really have to work hard to find a way to translate in the easiest possible terms what you can achieve, how you can help, and they have to be the same identical thing. Now, I mean, it's an example of materials, but this works for everything. I'm not a plasma physicist either, so this works in the same way when I talk to plasma physicists, to people in control, and so on and so forth. So you really have to know, to have very clear in mind what is in what are the ways that you think you can help, and they have to have very clear in mind what are their problems that they're trying to solve. And there is no, and there, it makes no sense to just like try to apply the coolest latest algorithm if there's just no use of that.
Right. Yeah,
Yeah.
exactly. Because like each of these algorithms or infrastructures kind of excel at a particular task, and you can't
Yeah.
just apply it randomly to answer any question, right? It doesn't work that way. Yeah. So I think it's more of just like the interdisciplinary component, right? Like getting it in some ways, it's almost you're right in making the analogy that you almost speak different languages, right? Like it's really hard to, because there's such specialization in each field, and the terminologies don't cross, right,
Yeah,
at some
yeah.
point.
I mean,
Yeah.
I found that to be the case even for astrophysics and fusion.
Hmm.
Like the terminology, even to refer to similar things, is just like the way people talk about things is different. I don't
Right.
know if it's probably like an emergent property of of the people that work in a
Yeah.
certain field.
Yeah, maybe we have to train an MI or ML algorithm on that to translate between different fields. Yeah,
Yeah.
yeah. But
So yeah, I think that that's why that's why I said that having an expert in the loop is always very important, because otherwise you end up doing things that are not useful, are not important, are not even like conceivable. For example, when I was during my PhD, I did an internship in a hospital doing statistical modeling of patients with high blood pressure, and I was doing, in my models, I was doing things that doctors would never do in their lives, like just
okay.
like taking patients on and off a pill depending on what is the threshold. And
Okay.
the doctor I was working with was like, no, this is absolutely not possible, because I mean, in hindsight, probably I should have thought about this.
Right. Right.
It
Right. But
doesn't make much sense.
right.
But these kinds of things do happen, and you need a domain expert that tells you, for example, what is so in some things are like, for example, the critical gradient model for gyrokinetic turbulence, right?
Mhm.
If naively you can just put everything in a regressor, and then you find that suddenly your fluxes are overestimated near the threshold, near
Right.
the critical gradient threshold, which is horrible for your core
Right.
because you over predicts your transport. So having that kind of domain knowledge that this is a sharp transition
Mhm.
really makes a difference in the way you conceive the machine learning models.
Right.
So this goes in the sense of this physics informed modeling, physics informed machine learning kind of framework.
Yeah, so what I hear is that it kind of goes both ways. Just like that domain experts need to understand machine learning isn't kind of like a silver bullet. It does require a lot of pre-work to be done in terms of not just the data, but then what question do you want to ask the data and all this sort of stuff. The other way around is also true that
Yeah,
the data scientists can't just like take a table of numbers and then apply a model to it. They need to understand a bit where the numbers came from and what do they represent, um, and like what is the, let's say, the state of the art of the field, so that they can use that knowledge in helping to develop the algorithm or develop the loss function at least,
yeah,
right?
but you see that becomes really hard, because
Mm,
at this point it's two people doing the job of one person.
right. Right.
Right,
Well,
let's say two people doing the job of one and a half people.
right. Yeah.
Okay, maybe.
Yeah. But like the communication is the hardest part, I think.
Yeah, there
Yeah.
is definitely um some optimization to be done. I don't know, like what is um I don't know how um you know how other, because, for example, if I think about, again, I'm coming back to the drug design
Mm,
community. They've managed to get a lot of momentum from the ML community behind the drug design objective, and it's been working really well. So it will
mm,
be interesting for us and the fusion community to learn about how these people um, have achieved that, to get that kind of momentum uh, from the um, from the ML community, which
right.
frankly we don't quite have. We don't
Right.
have quite the same reach of probably because our data is in a state, and
Mhm.
uh,
Yeah. Yeah,
yeah,
where it's hard to work with, and then there's also,
and
yeah.
we are also probably also that we definitely have less funding than people working in big pharma.
Mm,
So that also doesn't help. But I feel like we should definitely aim to do something similar. So gain that kind of momentum from the wider AI community,
right.
and work with them.
Yeah.
And it's also an interesting. It will also bring in interesting AI developments, because if you look at drug discovery, there's lots of interesting stuff in graph neural networks has
Hmm.
happened thanks to drug discovery, to applications to drug discovery. And I think that potentially, if I think of neural PDE solvers, for example, or control, we can also give them a tough nut to crack,
Right.
which will require new methods. And considering how fast this has happened, drug discovery, graph neural networks really weren't a thing before. I don't want to say anything, crazy, but I wouldn't think, before 2015,
Mm,
I, I don't think that people were actually doing much about drug discovery with graph neural networks, and now it's all about that in 7 years, and hopefully we can do something similar in a similar time frame or faster.
right. Yeah, absolutely. I think that there is definitely a lot of room for both the scientific, like the domain specific scientific community, and also then the machine learning community to, with these types of collaborations to grow. Yeah, absolutely. So one final thing, we're rounding up on our time. Maybe this is going to expose an entirely different conversation, but I have one final question to you. Do you think this touches back to the artificial intelligence stuff? Do you think we'll hit a point with all this data and all this machine learning, even in the field of, let's say, fusion, where the machine learning algorithm will know more than the scientist?
It depends what you mean by no.
Right.
Do you mean like
Let's say it because in terms of like trends, let's say in terms of prediction, right? Do you think we'll ever hit a point where the machine learning model predicts something that no human would have ever thought is a possibility and be right about it?
um well, I guess if you think about um imagine this scenario. You have a model, okay? It's a PDE, system of PDEs. You have a neural PDE solver that solves for that.
Mhm.
And the training set is, say, a hypercube, just a standard, grid on the hypercube. And the model kind of interpolates over this grid of parameters. Okay, but then maybe the query is at some point, one point in between this grid, and for
Mhm.
some reason, since we got plenty of bifurcations in Fusion, for some reason something happens in a particular data point that we would never have imagined, and maybe that model that we wouldn't have gone there, for example. But maybe the when, for example, if you plug this into a control system, okay, maybe the model wants to go in that particular point because it knows that in that particular point something interesting happens.
Mhm.
Namely, I don't know what
Yeah, it could be
something
any number
interesting
of
could
things.
happen.
Yeah, yeah, yeah.
Okay, but the model knows because it has all this high dimensional representation of the entire parameter space, which we just can't can't think about.
Mhm.
And so maybe something like that could happen. Yeah, but I don't know if I would think of a machine learning model that is able to essentially that knows everything about fusion and can make new hypotheses and test them and do everything. That sounds like AGI, and I'm not quite
Right,
sure we're there yet.
right.
But again,
Yeah.
as I said, I don't want to go there because I'm really out of my depth with AGI
Okay.
discussions. So uh, yeah, and it also is a massive speculation.
Well, I mean, this
Yeah.
question was a really speculative question, but
Okay. Yeah.
I think just to like get an idea of what you think the direction of this field goes, right? Because it would be interesting to know if it is a possibility, or at least to, let's say, preconceive a possibility where a machine learned model predicts something that all the scientists kind of look at and be like, it would be great, but like I don't have any idea whether that's possible or not, because that is sort of a prerequisite to people then trusting the machine. Like just like with the drug discovery, people look at the drug and be like, okay, should we try human testing on this? Right? Like
Well, obviously, first they
right,
go, there are lab trial, like there are like
right, yeah.
in vitro trials before going to humans. But
Yeah, yeah. But still somebody has to make that jump and like look at the result, the prediction from the model and be like, possible, but would have never come up with this, right?
I mean, yeah,
Yeah.
but for sure, right? That's if you think, for example, about um, yeah, the drug discovery example, that's perfect.
Mhm.
People just had no idea whether a particular compound would actually do the thing that the machine learning model promised.
Right.
And then you have some sort of like a few candidates, you do some screening of them, and you reduce until you take one to human trial. And I think so. Basically, this should kind of give us confidence that it can happen also in fusion. Why not?
Right, exactly. And
In
with
the end,
that,
those if you look also at AlphaFold, right? That's like those predictions for protein folding are uncanny. I know people
Mm,
in biology departments that use the prediction from AlphaFold, and they're very happy with that. And it would have taken ages for humans to actually make computations like with biophysics, sorry, computational biophysical models about those proteins,
mm.
and yet we trust those from AlphaFold, and they make sense to them. So we're gonna
So,
get the refusion.
right. Yeah. So what you're saying is there's a chance.
I
There's
hope
a
so.
hope.
I hope
Yeah.
so. Yeah. Yeah.
Okay, great. So then with that, Lorenzo, I'd like to thank you for coming on to this podcast.
Thanks for having me.
Yeah, it's been a great conversation. I've
Yeah.
learned a lot also from your what do you call it, descriptions of the differences between ML and
Was really
traditional
stimulating
statistics.
for me to it challenge me on some things, so uh, I hope the people in the public will take some of the things I said with a pinch of salt. uh,
Of course,
yeah.
I always tell to everybody that the podcast is not just learn for the public or for our listeners to learn, but also for us, the people involved in the conversation. So with that, to everybody listening, thanks for tuning in, and we'll see you on the next episode of Copy Breakdown. Bye.